Alright, so this is our AP Chemistry Chapter 19 Lesson Video Part 2, and in this video I'm going to cover Section 19.4 and 19.5. Alright, so we're picking up where we left off with entropy, so we're not done with that thing yet. So remember, entropy is denoted by S, so the molar entropy values of substances in their standard states are known as standard molar entropies and are denoted by S with a little like degree sign. So y'all, whenever you see like the degree sign, be it with S, H, G, any of those, that is denoting that you're at standard conditions. Okay, so the standard state for any substance is defined as the pure substance at 1 atm pressure and 298 Kelvin. So that means you pick what state it's normally at that temperature and pressure. Molar entropies for elements are not zero like delta H. So if you remember when we were doing standard heats of formation, I would say that the delta H, or the standard heat of formation of an element in its natural state, is zero. But entropy, that's not the case, because of course even substances in their natural state still have many microstates and can have entropies. The molar entropies are greater for gases than for liquids and solids, which makes sense. Molar entropies generally increase with increasing molar mass, and they generally increase with an increasing number of atoms in the formula of the substance. Because remember, more atoms, more bonds that can go through all those movements that we talked about. So, you'll recognize this formula. We've already used it before in Chapter 5, except we had delta H is delta H of your products minus delta H of your reactants. So now it's just delta S is the delta S of your products minus the delta S of your reactants. So you're going to see me pull some numbers. These are just coming from Appendix C in the textbook. So don't worry, I'll tell you what they are. If this was the AP exam, they would have to give you these numbers. Okay, they're not going to expect you to know these. I don't even know these numbers, which is why I got to get my answers out. Alright, so when I look up delta H for these numbers, for these substances, this is what I find. So for N, I got 191.5 joules per mole Kelvin. And for this one, I got 130.6 joules per mole Kelvin. And for this one, I got 192.5 joules per mole Kelvin. See, the important thing is, y'all, this is joules per mole Kelvin. That means the amount of moles makes a difference. So first thing I need to do is utilize my coefficients. Okay, so I know that delta S, I always like to just break it down and say products minus reactants. That's what I like to do. You don't have to do it that way, of course. All right, so this one, clearly all I would do is multiply it by 1. So I'm going to get joules per Kelvin, 191.5. This one, I multiplied this number by 3. And so I got 391.8 joules per Kelvin. And this number I multiply by 2. And I got 385 joules per Kelvin. And then, of course, I just do products minus reactants. So my product is 385 joules per Kelvin minus my reactants, which is the 191.5 joules per Kelvin, plus the 391.8 joules per Kelvin. And so once I put all that in, I got negative 198.3 joules per Kelvin. Just like that. Now, of course, you're more than welcome to just write it like where you would do 2 times this number right here equals this plus 3 times that number. You're more than welcome to write it like that. I write it like that in class a lot. This is just because I know you don't have the numbers, so I'm trying to show you where they're coming from. All right, so let's look at one that's almost exactly like this. And so I'm not going to pause it and assume you tried it. The first thing I'm going to do is give you the numbers. Then I'll assume you paused it and tried it. All right, so your numbers for these are 51 joules per mole Kelvin. For hydrogen, it's 130.6 joules per mole Kelvin. For aluminum, it's 28.32 joules per mole Kelvin. And for water, it is 188.8 joules per mole Kelvin. Okay, so now pause the video and try it. Now that you have them, don't forget to multiply by those coefficients. All right, so I'll assume you've done that. We'll look at it together. Okay, so this one just had a coefficient of 1, so it's just 51 joules per Kelvin. This one had a coefficient of 3, so I multiplied it by 3 and got 391.8 joules per Kelvin. This one had a coefficient of 2, so I got 56.64 joules per Kelvin. This one had a coefficient of 3, so I got 566.4 joules per Kelvin. All right, and then of course I know my delta S is my products minus reactants, so I just plugged in. So I have products 56.64 and 566.4. and then I minus my reactants. So I have my 51 joules per Kelvin and my 391.8 joules per Kelvin. Okay, so once I plugged in, I got about 180.24 joules per Kelvin. Okay, so again, y'all, this works just like when we did standard heat of formation, except instead of delta H's, I have delta S's. And again, they would give you these numbers because nobody expects you to know those by heart. All right, so let's keep going. If you have your textbook, you can find all these numbers in Appendix C, just saying, at the end of the textbook. All right, so entropy and the surroundings. For an isothermal process, which remember we talked about what that is before, it means temperature does not change. The entropy change is delta S is negative Q of the system over temperature. Okay, so we've already used this formula in the last video, we talked about it. Okay, ours just said negative Q of reverse. So this is just negative Q of system. For a reaction at constant pressure, you can exchange Q and delta H. And again, we've already talked about that in the previous video. Because remember, delta H is just your enthalpy change at constant pressure. Okay, and so you can use that same formula, so we don't have any practice with that because we already used that formula in the last video. All right, so section 19.5, we're going to go into Gibbs free energy. So spontaneous processes, remember, thermodynamically favorable, that decrease entropy are always exothermic. So y'all, if it's unfavorable to decrease entropy, but yet it's spontaneous, that means it has to at least be favorable with delta H. And so y'all, the thing you gotta keep in mind is when we're talking about thermodynamically favorable, we want a negative delta H, but we want a positive delta S. And then what you're gonna see in just a second is we want a negative delta G. So spontaneity involves both enthalpy, which is your delta H, and entropy, which is your delta S, and it also involves temperature, which is your T. Gibbs free energy is an equation used to determine spontaneity. So like I said, for the most favorable processes, we want negative delta G, we want negative delta H, and we want positive delta S. Because if you look, if we have a negative here and we subtract a positive, it's just going to become more negative. Okay, the problem occurs when one of these is not the way it's supposed to be. And then you might have to figure out, well, how does temperature change in order to make it spontaneous, or things like that. So if temperature and pressure are constant, then the sign of delta G means the following. If delta G is negative, it's a spontaneous or thermodynamically favorable process. If delta G is positive, if I said delta H there, I meant delta G. I feel like now I might have said it twice. If delta G is positive, the reaction is non-spontaneous, but remember that means the reverse is spontaneous or thermodynamically favorable. And if delta G is 0, that means the reaction's already at equilibrium. Okay, so that means the opposing rates are equal at that point. So let's look at how to calculate standard free energy change. So here we have a reaction, we have a delta H, we have a delta S. It's asking us, is the reaction spontaneous under these circumstances? So this is where we need to use our formula. So we know delta G is delta H minus T delta S. And once I know the sign of delta G, that will let me know whether or not it's spontaneous. The thing you have to be careful of is, though, for delta H, you will commonly see kilojoules, but for delta S, you will commonly see joules. So then in that case, you're going to have to convert one of them. And so in this case, let's see, what did I convert on here? In this case, I converted kilojoules to joules, which is odd. Usually I favor doing kilojoules. But that's okay, because my answer that comes up here will be in kilojoules, so you'll get to see either way. All right, and so what I did here was I went ahead and changed this to joules. So I ended up getting this right here. And so now I can compare those. Okay, so I plugged in. So my delta G is delta H, which I decided was 180,700 joules, minus my T, which is 298 Kelvin, times my delta S, which is 24.7 joules per Kelvin. So if you look, my Kelvin cancels, and so when I solved, I ended up getting a positive 173,339.4 joules, which of course is about 173 kilojoules if you chose to do kilojoules, but the important thing is it's positive. So is the reaction spontaneous? No. What would be spontaneous is the reverse reaction because delta G is positive. Okay, so you can see here, I have it in kilojoules instead. but it is not spontaneous. But like I said, on the AP exam, they would prefer you to say it's not thermodynamically favorable. Or you can say it's thermodynamically unfavorable. Okay, so y'all try this one. I will assume you've paused it and tried it, and let's look at it together. So it says, is the reaction spontaneous under these conditions? So we know delta G is delta H minus T delta S. All right, the problem is, of course, delta S is joules, delta H is kilojoules. So again, did I go joules to kilojoules? Nope, I went kilojoules to joules. That's so weird. I don't usually do that. So I changed this right here to 24,600 joules, and then that's what I plugged in. Wait, what did I do? Oh, I feel like I might have just done something. Oh, I'm looking at the wrong question. Oh my gosh. Okay, I probably should pause this and redo this whole thing, but I'm not going to. Okay, let's just keep on going. Sorry, I was looking at the wrong number on my paper, and I'm like, where did I get these numbers from? All right, so my delta H is 24,600 joules minus, and then I do my T, which in this case is 298 Kelvin, times my delta S, which is 132 joules per Kelvin. And so if you look, my Kelvin cancels, and so once I do my math, I got negative 14,736 joules, which of course, if you did kilojoules, you would have just gotten negative 14.7 kilojoules, but the important thing is delta G is negative. So if delta G is negative, then this reaction is spontaneous or thermodynamically favorable. All right, so hopefully you got that one right. And hopefully you didn't confuse yourself by looking at your own work, like I just did. All right. So next thing, we're going to do the same thing with delta G that we just did for delta S and what we've already done for delta H. So the standard free energy of formation is the free energy associated with the formation of a substance at standard conditions. So for solutions, standard state is 1 molar. Okay, so normally we talk about standard temperature and pressure being 1 atm and things like that, but the standard state for molarity is 1. So it's just your delta G of your products minus delta G of your reactants. So again, I'm going to be pulling numbers from Appendix C out of the textbook. So that's where all of these numbers are coming from. So it says calculate the standard free energy change of the following reaction at 298 Kelvin. So keep in mind, y'all, again, all of these, the units are kilojoules per mole, so I have to take into account the stoichiometry, the coefficient. So for P4, this number is just out of the textbook, is 24.4 kilojoules per mole. So notice delta H and delta G tends to be in kilojoules, but like I said, delta S tends to be in joules. All right, for this one is 0. For this one, it is negative 269.6 kilojoules per mole. So first thing I need to do is take into account my coefficients. That's just 1, so this is 24.4 kilojoules. This is 6, but it's still just 0. Anything times 0, of course, is 0. Multiply this one by 4, so I get negative 1,078.4 kilojoules. And then, of course, my delta G is just products minus reactants. Okay, so I just plug in my products. So I have negative 1,078.4 kilojoules minus my reactant. So 24.4 kilojoules plus technically 0 kilojoules. Obviously, you could leave out the 0. And so for this one, I've got negative 1,102.8 kilojoules. Just like that. Then it says, what is the delta G for the reverse reaction? Well, yeah, delta G works like delta H. If I flip the reaction, I just change the sign. Okay, so instead of being negative 1,102.8, it's just going to be positive 1,102.8 kilojoules. Okay, so Gibbs free energy works just like delta H, where you're changing enthalpy when it comes to that. All right, so you flip a reaction, delta H changes sign. You flip a reaction, delta G changes sign. However, if you flip a reaction, K, your equilibrium K, is 1 over, it's the inverse. Okay, so you gotta be careful of that kind of stuff. All right, so y'all try, oh wait, don't try this one yet. Let me give you the numbers first. Okay, so when you look up the delta G values, and remember, I'm gonna give you the kilojoules per mole, so don't forget to utilize these coefficients. Across the hall is so loud right now. I don't know if y'all can hear her. All right, so now pause the video, try this, and then we'll look at it together. So I'll assume you've done that. So the first one, I don't have to multiply by anything because it's just a 1. So it's going to stay as negative 50.8 kilojoules. Obviously, 0 times anything is still just 0. This is a 1, so it stays negative 394.4 kilojoules. And I multiply this last one by 2, and so I got negative 457.14 kilojoules. All right, and then of course my delta G, just like delta H and delta S, is products minus reactants. So then I just plug in. So my products are negative 394.4 kilojoules plus, I'll just go ahead and put minus because it's plus a negative, plus a negative 457.14 kilojoules. Whoop. Oh gosh, I can't see where my PowerPoint ends because it's just a black screen. So I don't, oh okay, I think I have plenty of room. I thought I was going to run out of space. All right, minus my reactants, so minus 50.8 kilojoules plus, of course, 0 kilojoules. But, of course, if you left off the 0, it doesn't matter. And so, hopefully, you got the same answer. I got negative 800.74 kilojoules, just like that. All right, so hopefully you got that right. So, remember, if this was on the AP exam, they would have to give you these numbers. Nobody expects you to memorize delta G's, delta S's, or delta H's. Okay, but they would expect you to know you do products minus reactants. Okay, so if they gave you those numbers, they would expect you to be able to solve. The other thing you gotta look out for is sometimes they'll give you the delta G, like for the whole reaction, and then they might give you this one, and this one, but then they might ask you to solve for that one. So you also need to make sure you know how to do that, okay? We'll look at some of those like on the practice sheet and study guide and things like that. Because they can ask you that for delta S, delta G, or delta H, because remember, they all work the same way. All right, so let's look at our next sample exercise. So it says, without using data from Appendix C, so for once we're not going to use that, predict whether delta G for this reaction is more negative or less negative than delta H. Okay, so y'all, whenever we have to do stuff like this, and they like to ask this kind of question on like the multiple choice, because remember, on the multiple choice, they couldn't use calculators. Okay, that's going to change this year, so now we don't really know what it's going to be like. But they couldn't use calculators. So see, since you don't have to actually do math, this is like a conceptual problem they would put on there. All right. So we can see that delta H is clearly negative, all right? And so what we need to do is figure out, well, what's going on with this delta S then? Okay, because temperature obviously is going to be positive. How do I know? Because it's going to be in Kelvin. Kelvin can't have negatives. Okay, so I know temperature has to be positive all the time, so I'm going to circle that because it's got to be, because it's Kelvin. All right, so let's look at what's going on with delta S. Well, on this side, I have 6 moles of gases. On this side, I have 3 moles of gases and 4 moles of liquids. So even though I have 7 moles, a bunch of them are liquids. So that means my delta S is going to be negative. So I'm taking a negative number and subtracting a negative, which really means I'm adding. So if you have a negative number and you add to it, it's going to become less negative. So think of it this way, like if I have a negative 4 and I minus a negative 2, because remember, that's really adding. That becomes negative 2. So see how now it's less negative? So if you ever have to, just pick some numbers to plug in. So in this case, delta G would be less negative because delta H is negative, but delta S is negative. Okay, so see, I wrote since the number of moles of gases decreases, entropy decreases, and this negative T delta S is positive, because see, we're going to have 2 negatives, so it's positive, which means that delta G would be less negative than delta H. So like I said, y'all, you got to get ready for those conceptual problems. A lot of you, you're really good at plugging in and doing a math problem, but once they ask you one where you don't plug in, it gets a little tricky. All right, so y'all try the next one, since you don't need any numbers. So I'll assume you tried it, paused it, done all this on your own, gotten it right, and let's look at it together. So it says, consider the combustion of propane to form carbon dioxide and water at 298 Kelvin. Would you expect delta G to be more negative or less negative than delta H? All right, so I know that delta H minus T delta S is my formula for delta G. So here, let's look at that delta S. Okay, so it's saying delta H is negative because we want to know, is it more negative or less negative than this? We know temperature has to be positive because it's Kelvin. So let's look. We have 6 moles of gases and we are making 7 moles of gases. So that's going to be a positive entropy. So if I have a negative number and I subtract another number from it, so think of it like this. I have negative 4 and I subtract 2, that becomes more negative. Okay, so in this case, delta G would be more negative because that entropy is positive, because we're going from 6 moles of gas to 7 moles of gas. But here it didn't ask me to explain, so I just put more negative. But if you needed to explain, like if this was a free response question, and you know how they always like you to justify your answer, you would justify by saying that delta S is positive, and so of course when you subtract from a negative number, it's going to become more negative. Alright, so hopefully again, so far, we've talked about entropy, so hopefully you're getting that. Okay, now we've kind of gone into Gibbs free energy, and we brought in the delta H from chapter 5, and so hopefully you're kind of seeing how those relate to each other.